Today's webinar will be 1 hour in length, and after it's completed, you'll be receiving a recording of the presentation within approximately 24 hours. I'd like to take this opportunity to introduce PhotoSat and today's presenter, Sam Rivet. Vancouver-based PhotoSat, founded in 1993, has invented a new technology to produce highly accurate satellite survey data. PhotoSat specializes in elevation surveying for civil engineering infrastructure projects and the planning and design of resource development projects. PhotoSat's expertise in geophysical data processing methods, combined with extensive experience, has resulted in the world's most accurate satellite surveying. PhotoSat's team has delivered over 1,000 surveying projects and produced data with better than 20 centimeter elevation accuracy. PhotoSat's goal is to provide engineering quality satellite surveys that shorten project timelines and eliminate survey delays. Today's presenter, Sam Rivet, is a registered professional mining engineer within the province of Alberta and has worked at the technical level in both the mining and civil construction industry. He was a tailings and project and efficiency engineer at CNRL's Horizon Oil Sand Mine. Following that, he worked as a mine consultant for a number of open pit operations. Prior to joining PhotoSat, he was a project manager at the earthworks portion of a highway construction project in Calgary. Recently, Sam joined PhotoSat as a sales engineer, lending his planning and operational surveying experience to the organization. And now I'd like to hand it over to Sam. Thank you.
Thank you, Jessica. I'd like to thank you all for joining me today. So the focus of this presentation is mine site survey errors that PhotoSat has seen while doing hundreds of mine site surveys over the past several years. So no mine wants to publicize problems and errors. So all these examples are intended to be anonymous. Given the importance of avoiding errors in mine site surveys, particularly mine tailings facility surveys, we believe that this is an important subject for discussion. We have seen some survey errors on the majority of the mine sites that we have surveyed, so these are not rare occurrences. If any of you recognize any of these examples, please keep that information yourself. So this is us, PhotoSat, Vancouver-based and founded in 1993 by our president, Jerry Mitchell. Since then, our expertise in geophysical data processing methods, combined with extensive experience, has resulted in the world's most accurate satellite surveying company. We have delivered over 1,200 surveying projects and produced data with better than 15-cent vertical accuracy. Okay, so a quick overview of the presentation. We're going to talk about the plan view and scatter plot format that we're using consistently to represent the data. We're going to give examples of vertical offsets seen by PhotoSat, give examples of drone data seen by PhotoSat. We're going to talk about custom mine grids. Then we're going to go over projections, datum, custom geoids, and survey benchmarks in tectonically active areas. And then finally, we're going to talk about surveyed data accuracy and volumetrics, followed by a Q&A period. Okay, so in every position I've held as an engineer, survey data has been critical at every stop. When I was in tailings, trying to plan and monitor a 10 to 12 long kilometer earthworks dam, I needed accurate as-built data all the time of the structure. It was just too big to visually monitor on foot, and the mine's waste material balance was too tight to make mistakes. We needed to know exactly where and when and what material was needed to stay ahead of minimum freeboard, where to move the lines to minimize relocations. What is the dam's capacity today, and is it good enough for a 100-year storm event? How does what we're building compare to what's been designed? The downside of not knowing was huge. When I was in mine projects, trying to run pipe through the site, build access road or clearing trees, I was constantly looking for current, accurate surfaces and relevant as-built. My planning, my costs, all the logistics. The scope of work itself was built off the information I was pulling from the current surveyed surfaces, the designs, and the as-builts. As a dispatch engineer, all production every month had to be survey reconciled. The quality of our reporting, not only internally, but to the government and investors, depended on the accuracy of our data. And if there was a disconnect between your survey data and your dispatch data, the consequences were far-reaching. This is why we believe in the importance of the accuracy of your survey data. Okay, to start, I'm just going to run you guys through some real examples we've dealt with over the years. The first example here is from an open pit metal mine, whose location and name will remain unknown. Like all examples used in this presentation, once again, we're using real data, real situation, but all the details have been removed for confidentiality reasons. Okay, to represent, quantify, and speak to the survey issues in this presentation, we've chosen to represent the survey data on a straightforward plan view map, an associated scatter plot measuring the differences in vertical elevation. Okay, so on top here you have a standard plan view map. Okay, in this example, the plan view map will be represented in the north-south view like this, with the corresponding axis line for reference. Okay, then we'll just add to this the survey data, the points that we receive from customers in each case. The X's here can represent points in some situations or clusters of survey data points. For the purposes of this presentation, it's immaterial. Okay, these survey points are what the mines send us that we use to tie our surveys into their existing data and dial in our deliverables to that 10 to 15 centimeter vertical accuracy level. Okay, in this situation, these points to the south here correspond to the initial set of data that the mine sent us. Okay, these points here in the middle represent the second set of survey data that mine sent us. And then finally, these points in the north, the third set of data. This fourth set of data, suspiciously in red, you can see here added to the plan view map. Okay, now we're going to visualize these data sets on a scatter plot outlining the elevation difference between the data we received and the PhotoSat elevations of that exact point at that exact same location. So this is something that can only be done in retrospect because we need our final product to exist to compare the elevations. Okay, the scatter plot on the x-axis has the northing of the points, so you can locate them in space versus the plan map. The points more to the north will be further down the x-axis. Okay, on the y-axis, it's measuring the difference in vertical accuracy or the vertical elevation between what was supplied to us and what our produced satellite survey surface showed in the end. So for these graphs, a 0 y-axis value or any point along the x-axis itself represents an elevation reading identical to what we have. So there is an assumption here that our data is considered correct, and the variance in elevation from it is essentially error or mostly error. So as an organization, we've conducted over 1,200 major surveying projects in a 27-year span. We've published 50 accuracy reports since 2008, so we can credibly say in these situations our data is accurate. Okay, as a quick aside, just to give you some background on PhotoSat surveys, they're instantaneous. They take a minute. They do snapshots of areas up to several hundred square kilometers. The PhotoSat elevation accuracy is consistently better than 15 cents on average. The accuracy is measured on areas of bare ground with slopes of less than 20% grade. On areas of steeper slopes, the accuracy is usually better than 50 cents on average. Prior to 2017, PhotoSat published many satellite surveying accuracy studies. 12 of these accuracies are shown on this slide, and they're available on our website for your review. Since 2017, we and our customers have measured our surveying accuracy on hundreds of mine site surveys, and since then, our accuracy measurements have been consistently better than 15 cents vertically on average. This 15-cent vertical accuracy RMSE number refers to the accuracy of each point on a 1 by 1 meter PhotoSat mine site survey grid. The measured accuracy of volumes determined by PhotoSat surveys are generally in the range of 2 centimeters times the surface area of the measured volume, and this will be discussed in greater detail later. Okay, so just getting back to our example, we're going to take the first data set and send it to the scatter plot. You can see the points to the south have a lower northing. Okay, then we're going to add the second data set, the third, and finally the fourth here. Okay, so what happens here is very common and it happens in what we would estimate is 20% of all our jobs. We receive conflicting survey data from the mines with different vertical offsets. Not only is the data off, but the data is off in different ways. Okay, so having this type of conflicting data is going to lead to problems. You can see here the first set is clearly 70 cents too low, and the second set 60 cents too high. Or sorry, the third set 60 cents too high. The second set here actually isn't too bad. It does split the difference between the two, but you have no way of knowing this when you get three conflicting sets of survey data. Finally, we asked them to carefully reshoot more survey data to resolve the control issues. And here you can see the fourth data set is aligned well with the second data set, and it's what we use to register our data. Okay, another example of conflicting data sets. This time, data supplied to us by a large open pit silver mine. Instead of using the northing as reference, we're going to be using the eastings. Once again, plan view map up top there. Okay, so we're going to have the scatter plot on the bottom, measuring the difference between the supplied survey data that was sent to us minus the PhotoSat elevations at that same location. And you can see this time, the x-axis is the eastings. Okay, we see here the first set of data points in plan on the scatter plot in gray. Okay, and we have a clear 23-cent positive vertical offset of these initial survey points. Then we add the second survey data set supplied to us here in blue. And once again, a consistent positive vertical offset, but this time of 83 centimeters. So two situations here where the survey data has two clear different vertical offsets. At the time, we don't know this. We can't establish if one is correct or not without investigating further. Okay, it turns out the first set of control data, the ones in gray, were from survey monuments. And the survey monuments look something like this, rebar sticking out of the ground. This is not the survey monument itself. It's just a photo used for illustrative purposes. This is actually a survey monument from somewhere in Georgia. Okay, but it turns out this monument is exactly 23 centimeters in height. Okay, same situation with the second set of survey data. They were shots of concrete benchmarks that looked something like this. Okay, and they were 83 centimeters in height. So clearly here, there was a communication tracking issue where we were being told we were being supplied with top of ground elevations, but it was actually top of monument elevations. Okay, this seems like a silly situation, but not accounting for the height of monuments, base stations, or the height at which you're installing a receiver on a piece of equipment is a very common error that I've seen many times in my career. And this could lead to a number of problems, particularly if you don't account for equipment height when installing a GPS receiver on something like a production shovel. That vertical offset might throw off where you think your bucket is versus the geological model. Suddenly you're in a waste block, but the display in the operator's cab tells him he's in an ore block, and that can lead to a number of situations, namely sending good ore to the dike and waste to the plant. Okay, here's another example of conflicting survey data with vertical offsets from another large open pit mine. Okay, they sent us 10 data sets to help us tie in our first survey to their site. Unfortunately, once again, the accuracy was inconsistent and conflicting, but there's obvious clusters or groupings here with the data where the verticals offsets align. And you can see once again that depending on where and when the points were picked up, they used different control, different base stations, and the lack of consistency created 10 data sets that had bad relative accuracy. So they're not consistent with reality, and they're not consistent with themselves. Turns out the dark purple set here was actually fairly accurate, but there was no way of knowing this until you'd analyzed all the data thoroughly. Okay, another example here can be seen from another open pit mine survey project we did. Okay, we were sent a large amount of survey data that covered their entire site. You can see the points in plan view here. It spans about 5 kilometers. Keeping in mind we're benefiting from hindsight here, but as you can see from the scatter plot, the vertical accuracy of the data is all over the place, and there isn't a clear issue that's apparent. So after a lot of data elimination and investigation, we could isolate these areas and once again establish you have multiple types of offsets tied to where and when the survey was taken. Look at this area in the red circle to the west. This data is all adjacent but presents 3 clear and different offsets. Not only is this data not accurate in an absolute sense, but the relative accuracy between the data itself is poor. You have a 2 to 3 meter swing from the orange to purple data offsets, and they're essentially in the same location. And this is a structural byproduct with constantly building up your survey data with many components, sources, and surveying methods. You're creating a lot of moving pieces to maintain, and you're exposing yourself to errors every time you add to it. And if a component is compromised, that error is going to propagate throughout your entire data set over time. We take instantaneous snapshots of very large areas when we survey. Given that all the data is acquired at once and not patched together over time, our data is very self-consistent. No localized errors. There's only one component, one data set. So if it's broken, the whole survey is off in an analogous fashion. But it's not just the speed of the process, it's the amount of survey data acquired in one shot. Not only is the data consistent with itself because of the survey timing, but we always have enough information for direct comparison of the PhotoSat survey to all of the different mine survey data sets that they provide to us, and identifications of the offsets like this is possible. Limiting unnecessary and redundant survey data is very important. You need to be consistent and structured with what survey data you're incorporating into your planning, reporting, etc. 2 surveys of the same unchanged area are going to vary. The variance might be minuscule if the methodology is the exact same, but when you're combining a number of surveying methods, the methodology is going to vary greatly, and 2 surveys of an unchanged area will create 2 surfaces that make it seem like there was activity there. I was working, once again, for a large open pit mining operation as a consultant. I was brought in because their month-to-month reporting was completely broken. They couldn't accurately report on mined ore tonnages using survey data to the plant, to the government, or to upper management, and load counts just don't cut it when the numbers are official. Their survey-adjusted load factors on their equipment swung wildly month to month, from 50% more than the nominal payload to half of what the truck could carry. Same erratic results with their survey-reconciled plant recoveries. Sometimes it was above 100%, sometimes it was 60%. Either way, not realistic. Okay, so the main reason for these wild variations that were impossible in real life was their month-to-month survey totals were wrong. They were manually surveying their pit sometimes, scanning at other times, depending on the surveyor, and the different methods yielded different results. But they were also resurveying inactive areas and updating them in their surfaces needlessly. So, for example, first month, the surveyor comes in, he surveys this face, he comes up with the orange line. Okay, so now that wasn't accurate. He's taken extra volume versus where the mine face actually is. But then the next month, another surveyor is going to come in, he's going to resurvey it, and he's going to come up with the blue line. So not only did you lose that extra survey volume that you erroneously took in the first month, but now you've lost additional volume in the second month that you had probably actually mined out. And this is creating massive swings. So in the month where you took the orange volume, your survey adjusted load factors, your total ore volume is going to be artificially elevated, and then you're correcting it, overcorrecting it, and your total ore volume is going to be underreported. That being said, I've also been in situations where hundreds of thousands of tons of material just doesn't get surveyed because operations go the other way. Everything's geared towards just making it work, and things get missed. Okay, moving on. The following examples illustrate erroneous drone data we've received over the years. Now, this doesn't serve as an indictment of drones or the data they produce, but we do receive this type of data all the time from clients. I'm not a drone operator or qualified to speak to the causes of the error, so I'll simply go through what we've observed. Okay, so same format to represent the data here. Plan map up top, where you can see the data points in blue, and then the scatter plot of the elevation difference of the data that was supplied to us, minus the PhotoSat data elevations at that same point. Okay, you can see here a drone survey of a tailings storage facility. The drone survey elevations are 2 meters too high in the south, 80 cents too high in the center, and 1 meter too low in the north. So kind of all over the map and just varying depending on where the drone was. Okay, here's another example of a drone survey of a tailings storage facility that we received from one of our clients. As you can see, as the survey moved west, the results became very inaccurate, getting to 2 meters too low on the western side. This is about a 3-kilometer area. For the eastern points, more accurate, definitely more consistent, but still kind of all over the place. Okay, another drone survey of a tailings storage facility. Once again, not sure what happened here, but this data has vertical inaccuracies ranging from 6 meters too high to 7 meters too low. So this is pretty bad. You can see the entire surface is just curled up. 13-meter vertical swings. Obviously, this is not usable data. Okay, same idea. Another drone survey of a tailings storage facility. As you can see, once again, as the data goes to the east, the accuracy begins to lose all tightness. And you can see a pattern here. As the survey's area expands, the data on the outskirts tends to be compromised. Okay, another drone example, this time of a pit. You can see the drop in accuracy here from the shots at the pit crest versus the shots at the pit bottom. Also, you notice a consistent tilt going east to west from the top of the pit points to the bottom of the pit points. So the base of the pit is obviously very important. All your geological drilling, all your planning, all your net present value analysis has gone into establishing where the base of your pit should be. You've also likely submitted pit shells to the government, so I believe you're going to be held to mining in that configuration. So introducing pit surfaces, survey pit surfaces with a base that is off by 2 meters, 3 meters into your work is going to create a number of problems. You know, there may actually be a physical constraint to digging deeper, like a basal aquifer you're trying to avoid. You know, you don't want to accidentally flood your pit because you thought you were 5 meters higher than you were. Once again, alignment with your geological model is going to be off. You might end up in the wrong block, and then you can really start to affect the plant once you start losing that continuity between grade information and production planning. And you're also probably going to either have to go back and either backfill or take out a thin lift of material to reconstitute the proper planned pit bottom. Okay, once again, a drone survey of a tailings storage facility. As you can see, distinct surveys yield different vertical offsets. So every time you do a different survey, you're getting a different vertical offset. And you're here again creating a survey that is only not self-consistent, but isn't accurate in the absolute either. And that is going to make it very hard down the road to figure out what, if any, of this survey data is usable for planning and monitoring. Okay, moving on to custom mine grids. So many of our clients, many mines, they have their own specific coordinate system they like to use. This means all the survey data needs to be converted from a universal system like UTM to that specific grid. You see here some points representing survey monuments that we received from one of our clients. Okay, but these transforms from universal systems to custom mine grids, they can get fairly complicated. It isn't just about a horizontal and vertical shift. There's a rotation, a scale factor component to as well. Look how unintuitive the coordinate relocations appear in this map. Okay, so these arrows and distances represent what it takes to go from UTM to the mine grid in this situation. These are real values. You can see here on the eastern side on the right, to transform it, you're going straight down 6.1 meters. Okay, but then by the time you get to this 3.5 meter point, you have to go like 45 degrees west. And then by the time you get to the east, you're going in a completely different direction and different distances. Okay, and what often happens is that the nature of the transform may change over time. and even varying versions of the transform exist simultaneously within the site. In isolated situations, maybe the lack of transform accuracy and consistency doesn't affect your project because you don't know there's a mistake yet, but over time, it's going to catch up with you and it's going to create a mess of data. Okay, at this mine, 3 different business units had 3 different transform systems that they were concurrently using, and the transform systems didn't align with each other. So if you were in A and you're trying to transform from UTM to the A system, you couldn't use it in B because the point would be at a different place. So when we first did a survey of their site, we immediately had to clean up this transform situation as it was untenable. Okay, so here I've obscured any specifics, but this polynomial transform was determined and works now throughout their entire site, and they're using it for all areas of the mine. And you can see that it isn't straightforward. There's a horizontal translation, a rotation angle, a center of rotation, and a scale factor, and they all need to be determined and translated into these transform equations. I know at a mine I used to work at, there were multiple transform spreadsheets floating around to transform coordinates from UTM to the mine grid, and they didn't produce exactly the same answer, but we felt it was close enough and continued using both. It was probably close enough to dig some sump somewhere, but was it close enough to bury a gas line and find it later? Which brings me to my next point. When I see transform issues like this and their impacts, the first thing I think of is critical as-built data. So over the years, many contractors, many people, many business units are going to be installing and burying water and gas lines throughout your site. Now, every line is or should be getting as-built prior to burial. But when you have these non-aligned transform systems, you don't know if anything's accurate. Did the guy who buried this line 5 years ago use transform A, B, or C? Did they pick it up initially in UTM, then transform it? Was it the reverse? Did different people use different transforms as they picked it up? The end result is probably going to be a situation that I've seen many times, is where you go to expose the line because you're working in that area several years later, and the line isn't there. Now your project's running late, and you're eating up budget paying for a hydrovac to pothole all over the place, hoping you get lucky and find the line. Okay, another example of a transform system gone wrong. This is from one of our clients, where they transformed their GPS and LiDAR surveys into the mine grid, and it was 78 cents off. Okay, this next example was provided to us by a client who thought they were getting distinct and complete drone surveys and photos from consecutive months, so full monthly updates. So we took the client's data and compared his surfaces and his photos to what we did, and only after that they realized that something fishy was going on. Okay, so this is a drone survey of a tailings beach, and this is the associated photo from it. What you see here is the center of the tailings beach. So we could later determine this update from April had updated data in the middle. You can see here in April. But the area to the left was data from March, and the gray material on the right is data from an unknown source. Now, it's not unheard of to patch together information as you receive it, but remember, this was being supplied to our client as a full monthly update, so new data throughout. Okay, May, same situation. Middle portion is still April. Area to the right has now been populated with new May data, which is good, but the area to the left is still March. Okay, then we get to June, and the entire surface, or a lot of it, has been updated with new June data, which is good. Unfortunately, when you get to August, June data disappears, and the left portion is once again March, now 5 months old. And then you can see the same situation in September and October. So now our client is in a situation where he believes he has full and accurate monthly data. He's using it to plan without any idea that large portions of this surface are 7 months old. In this situation, he'd be better off having holes in the data than having information he thinks is current, which is actually very outdated. What happened with the June data? I'm guessing it was completely compromised. They didn't want to admit to it, so they shelved it before anyone would notice. It gets even worse in that they mess with the color and contrast of the satellite photo to hide the patching, and also the surface itself associated with this photo. which should align, was quilted together, but quilted together in a slightly different way. It seems like the data they were collecting was getting compromised on and off. They didn't want to admit to it, so they started faking it. And as with a lot of situations, when it comes to lying, the cover-up starts to become worse than the crime, and it leads to more and more deception. Okay, just moving on to elevation reference errors. So it's important to know the vertical reference system for the data for each mine site. PhotoSat frequently receives mine survey data with undefined or unknown vertical references. Often it's not clear if the mine site's elevations are ellipsoidal, so relative to an ellipsoidal approximation of the shape of the Earth, or geoidal, relative to the geoid model of the Earth. Elevations relative to an ellipsoidal model, such as WGS 84, can be tens of meters different from elevations relative to a geoidal model, such as EGM 2008. Elevations relative to different geoid models can be different by more than 1 meter. Okay, the true geoid is a gravitation equipotential surface that corresponds to the mean sea level over the oceans. Over land, the geoid is estimated with a geoid model, and there are a variety of geoid models. This diagram shows surface topography, 2 different ellipsoids, WGS 84 and GSR 80, and 6 geoid models. Each of these vertical references will provide a different elevation for a point on the surface. Okay, this table shows the differences in elevations in Ottawa, Canada, my hometown, for 6 different geoid models. A perfectly accurate survey relative to the GSD 91 geoid will have an elevation error of 89 centimeters if it's incorrectly labeled as being relative to the CGVD 28 geoid. Okay, you also have to be aware of custom geoids, often described as height above sea level. So PhotoSat worked on a project in South America in which there were 3 existing sets of survey data, each with over 50 GPS survey monuments. On each survey, the elevations were defined as heights above sea level, SNMM. Interestingly, although the 3 surveys covered approximately the same area, none of the surveys included the same monuments, so there was no way to directly compare the elevations. When PhotoSat tied these 3 surveys together with a satellite survey, we discovered that each of the surveys had a different definition of height above sea level, and none of the surveys described how they had arrived at that height above sea level definition. The elevation differences between the 3 surveys varied up to 1.5 meters in elevation. So when you see elevations labeled as sea level or SNMM, and these terms aren't clearly defined, beware. Okay, quickly touching on survey benchmarks in tectonically active areas. So in tectonically active areas of the world, survey benchmarks often move up to 2 centimeters horizontally and 1 centimeter vertically each year. So a 25-year-old survey can be different by 50 centimeters horizontally and 25 centimeters vertically from a current survey of the same benchmark. Survey data is sometimes adjusted to a particular year, such as Surgas 2016, where the survey data from all the years are adjusted to the locations, kind of like currency, your baseline in it. Okay, so we've been through a lot of examples illustrating, demonstrating the prevalence of vertically offset survey data in this presentation. Obviously, having a poor handle on things like buried lines, pit configuration, tailings beach height is going to have a variety of effects on your mine. You know intuitively, inaccurate information is eventually going to catch up with you, but it's difficult to quantify. But one thing we have quantified is the impact this vertically offset data is going to have on your volume calculations. Okay, let's take a closer look at this with this tailings beach volume example. Okay, as stated or inferred throughout this presentation, the strength of our surveying is everything is captured in an instantaneous snapshot. That enables PhotoSat to precisely measure the survey accuracy by comparing the new PhotoSat survey to all the existing ground survey data, but also all the previous PhotoSat surveys for all unchanged areas of the mine. You have way more information to reference to make sure you're correct, and all the information we're producing is in one continuous data set, so there can't be localized error. This adds a level of reliability and repeatability to the data and makes it very self-consistent. There won't be 5 to 6 different vertical offsets in our data. If there is an offset, there can only be one, and it would be easy to determine. This allows us to do accuracy studies of our data by studying what we produce versus the supply data in the inactive areas. And we're always picking up these inactive areas because of the scale of our surveys. Okay, so for this June survey of a tailings storage facility that you see here, we wanted to quantify the accuracy of our data. Okay, so we determined the root mean square error of the vertical accuracy of our data versus the existing control in the inactive areas. Now, the RMSE measures how much error there is between the two data sets. Residuals are a measure of how far from the regression line the data points are, and the RMSE is a measure of how spread out these residuals are. And we also wanted to determine the mean error, so just the average of all the errors in the set. Okay, so we performed the analysis for the June survey, and we determined that we had a standard deviation, or RMSE, of 11 centimeters and a mean of 1 centimeter. So because the RMSE error is pretty symmetrical in both the positive and negative directions, because we don't have a biased vertical offset, it averages out to 1 centimeter. Okay, we then performed the same analysis on the August surface. The two surfaces were interested in running against each other. And once again, we had an RMSE of 11 centimeters. So you're anticipating here that our vertical accuracy is plus or minus 11 centimeters to the control data. But when you average them out, because of the symmetrical nature of the error distribution, the mean is 0 centimeters. Okay, so I'm not smart enough or even have the time to run you through this proof to prove that it's correct, but this is a formula to quantify volume error based on RMSE of your data sets and the difference in your mean. So if you consider that the checkpoint data in this situation is right in the absolute, mathematically it's been determined that the standard deviation and mean averages of our surface data set versus the checkpoint data set, then your anticipated error is going to depend on E1, E2, offset, and area. Now, E1 is the RMSE of the June surface. E2 is the RMSE of the August surface. Offset is the difference in the means. So in this situation, one of the mean errors was 1 centimeter, one of the means errors was 0 centimeters, so the difference between them is 1 centimeter. And the area here is just the area of interest where you're running your volume. Okay, so let's take a closer look at this tailings beach that we're interested in, where we have our June surface, we have our August surface. You can see here an isopack illustrating where material was placed, where material was taken, warm colors placement, cold colors cut. So we have here a surface area of 800,000 square meters, and the June to August tailings placement volume that we got when we ran the surfaces against each other was 740,000 cubes of tailings placed net. Okay, so let's take those variables and plug them back into our equation. So we have here an anticipated error volume of 8,000 cubic meters on 740,000 cubic meters of tailings placed. So we're within 1%. I would say that is pretty accurate. So because there aren't any artificial or localized offsets, paired with the fact that the June and August data are consistent with each other, the volume error is very low. Okay, but what happens if there's an erroneous offset in the data? The means of the surface area distribution will be asymmetrical and inconsistent, i.e. in situations like these, our first example, where varying vertical offsets are found in the data. Okay, you can see here you have a 70 centimeter vertically offset negative value, and that's going to skew negative when you do the distribution. Same situation, you have a 60 centimeter vertically offset GPS data, and that's going to skew positive when you do the error distribution. So that's going to create two means that are very far away from each other. So the difference between them is going to be a much larger number maybe 10 centimeters, maybe 20 centimeters, maybe even 5 centimeters. Okay, and you can see here in the formula, one of the most important factors in anticipating your volume error is the offset, because that coefficient is directly applied to the area, and the area is by far the largest, is going to be the largest number in this equation. So so in the initial example, our offset was 1 centimeter. If we go back to this example, you know, your 70 cents too low on average, your 60 cents too high on average. So your mean error here is could be like 30 centimeters. Your mean error over here could be 30 centimeters. So now you're going to have a mean offset of 60 centimeters times the area, as opposed to 1 centimeter times the area. It's going to make a huge difference. So you can see here, if our survey offsets, so the difference between the means of the errors is 10 centimeters, suddenly our volume error goes up to 80,000 cubes. 25 centimeters, 200,000 cubes. 50 centimeters, 400,000 cubes. And that's a 50% error on your volumes. And looking at this distribution right here, if you ran these two surfaces against each other, you're probably going to be close to that 50-cent mean offset. Okay, this is another example. This time, it's a much thicker stockpile than initially, so the errors aren't going to, the surface area to total volume is much lower. But still, if you have a 2 centimeter offset, as we typically do with our data, you're going to have a 10,500 cubic meter volume error. But once that becomes 10 centimeters, 20 centimeters, 50 centimeters, suddenly we're talking about 250,000 cubes of material, and that's a substantial amount. And this is just same stockpile, but in section view.
On behalf of Vegemine and PhotoSat, I'd like to thank everyone for attending the Mindite Surveying Pitfalls and Errors webinar. We'll be receiving a link to a survey shortly, and we'd greatly appreciate everyone's feedback on today's webinar to enable us to continue to develop effective and relevant webinars and courses. And yes, on behalf of everyone here, we'd like to thank Sam for his presentation. Thanks, everybody, and we hope that you have a great rest of your day.